отмашку, да? Можно? Okay, at the previous lecture, at the end of the previous lecture, we introduced the notion of equicontinuity, and we made some very basic and simple observations related to this notion. So let's now recall the definition. If we have two topological vector spaces, x and y, and a set S consisting of continuous linear maps from x to y, then we say that S is equicontinuous if for every neighborhood of 0 in y, say v in y, there is a neighborhood of 0 in x, say u in x, such that every map from S takes u to v. P of phi of u is contained in v. So again, the point here is that the same u works for all maps in our family. So for a single phi, this property means precisely that phi is continuous at 0 or equivalently continuous. So the point is that the same u works for all maps in our family. And equivalently, this property can be stated as follows: for every neighborhood of 0 v in y, the intersection of the preimages of v under for all maps in S is a neighborhood of 0. Neighborhood of 0 in X. So we observed that in the special case where X and Y are norm spaces, the property of equicontinuity means precisely that the set is bounded for the operator norm on the space. So if X and Y are norm spaces, then L of xy is also a norm space for the operator norm, and this property is equivalent to the boundedness of S. And in the general case of arbitrary locally convex spaces, we observed that every equicontinuous set is bounded for any reasonable topology on this set. More exactly, we proved that this is our proposition. If S is equicontinuous, then for every family B of bounded subsets of X, S is bounded for the topology of uniform convergence on B, on elements of B. So let's recall that this notation means that we equip the space of linear operators from X to Y with a topology of uniform convergence on B. So if we compare this result with the setting of norm spaces, we come to a natural question: how about the converse? So in the case of norm spaces, these two properties are equivalent if we take the family of all bounded sets. In the general case, the converse is not true, and we'll give some counterexamples later. But on the other hand, it turns out that if X is nice enough, then the converse is true. So now we come to the following, to a very special class of locally convex spaces. So we start with the following definition. If X is a locally convex space and B is a subset of X, then we say that B is a barrel, бочка in Russian. Что? Еще раз. Где? Нет, это... Не-не-не. Это просто, well, this is the space L of xy of all continuous linear maps from X to Y equipped with the topology of uniform convergence. Topology of uniform convergence on elements of V. So as a vector space, this is always the space of continuous linear maps from X to different locally convex topologies. For example, we can take the family of all bounded subsets, and this will become a locally convex space. Or we can, for example, take the family of all finite sets. And as a result, we get the same space, but equipped with the topology of pointwise convergence. And there are many intermediate options. For example, we can take the family of all compact sets. And as a result, we get the space equipped with the compact open topology. And so on. So there are many nice concrete examples of such topologies. And well, when we discuss duality of locally convex spaces, we'll consider such topologies in more detail. Okay, so now if we have a subset B of a locally convex space X, we say that B is a barrel. If B is closed, absorbing, and absolutely convex. So if you take a special case where X is the real plane, R2, and if you'll try to imagine how a barrel on the plane looks like, you'll shortly come to the conclusion that every barrel should contain a neighborhood of 0 in the plane. And locally convex spaces with a special property have a special name. We say that X is barreled boczyczne. X is barreled if every barrel in X is a neighborhood of 0. Yeah. Well, let's recall that when we say a neighborhood of a point, we adopt the convention that a neighborhood is not necessarily open. A neighborhood of a point is a set for which this point is an interior point. So there is a smaller open set which contains this point. Okay. How about examples? Well, many natural spaces are actually barreled. For example, we have the following proposition. All Fouché spaces are barreled. By the way, before we prove it, let's look once again at the definition. The definition is, well, it's important to compare this definition with the definition of Bornological spaces. So let's recall that we say that locally convex space is Bornological if every Bornivorous set, absolutely convex Bornivorous set, is a neighborhood of 0. And Bornivorous means that it absorbs all bounded sets. Here the situation is similar, but not exactly, because, well, a barrel is absorbing and absolutely convex, but it doesn't have to absorb all bounded sets. On the other hand, a Bornivorous set is not necessarily closed. Absorbing means that, well, if we take, let me write it down here. So if X is a vector space and B is a subset of X, we say that B is absorbing if it absorbs every point. So if for every X in X, there is constant C such that X belongs to lambda B whenever lambda is big enough. This is the definition of an absorbing set. So if it absorbs all points, and a Bornivorous set by definition absorbs all bounded sets. So this is, looks similar to the definition of a Bornological space, but not exactly. So a barrel is not necessarily Bornivorous, and the Bornivorous set is not necessarily closed. So Fruchsee spaces are barreled. Why is it so? Let's take a barrel. So suppose that X is a Fruchsee space, that is a complete metrizable locally convex space. And suppose that B is a barrel. Well, since it's a barrel, it follows that X can be written as the union of the sets NB over all natural numbers N. So now X is a Fruchsee space, and we may apply Bayer's category theorem. So not all of the sets and not all of them are nowhere dense. At least one of them has the closure of at least one of them has a non-empty interior. There's an N such that the interior of the closure of an B is non-empty. But B itself is closed, and so NB is also closed. So this means that the interior of NB is non-empty. But since the multiplication by N by natural number is obviously a homeomorphism of X onto itself, this implies that the interior of B itself is non-empty. This is not exactly what we wanted to prove. We wanted to prove that 0 sits in the interior of B. Well, let's take any point, X in the interior of B. Then clearly 0 sits in the interior of B minus X. Just use translation by X. B minus X is contained in B minus B. And since B is absolutely convex, B minus B is just 2B. So as a result, 0 sits in the interior of 2B. And since multiplication by 2 is a homeomorphism, we deduce that 0 is in the interior of B. Мы используем метризуемую, когда теорему Bayes воспользовались. So Bayes' category theorem normally is proved for complete metric spaces, for complete metrizable topological spaces. So, of course, there are some more general topological spaces where this theorem holds, but the classical setting is the setting of complete metrizable spaces. Okay, so as a result, B is a neighborhood of 0. On the other hand, a normed space is not necessarily barreled. This is an exercise for you. Well, space is barreled, of course, because the Fruchsee space is barreled. I'll not give you any hint here because, well, all reasonable examples of normal spaces which are not complete, they are not barreled. So take any classical norm space which is not complete, and most probably your space is not barreled. Okay. Are there any other natural examples? Yes, there are, because it is to show that the property of being barreled is stable under forming inductive locally convex topologies. If we have a family of locally convex spaces, Xi, family of locally convex spaces, and if X is a vector space, equipped with an inductive locally convex topology, with the inductive locally convex topology generated by a family of linear maps, phi I from xi to x. Then, if all the spaces xi are barreled, then x is also barreled. And x is also barreled. The proof is based on our earlier result on neighborhoods of zero for the inductive locally convex topology. Well, indeed, suppose that B is a barrel in X. Then clearly the preimage of B under every map phi I is a barrel in Xi. For every I. Well, clearly the preimage of a barrel is a barrel, just by the definition of a barrel. The preimage of a closed set is closed, the preimage of an absolutely convex set is absolutely convex, and the preimage of an observing set is observing. So it is a neighborhood of zero. A neighborhood of zero in Xi. And let's now recall that if we have an absolutely convex set in X, such that all its preimages are neighborhoods of zero, then the set itself is a neighborhood of zero. This is a neighborhood of zero in X. This is just a standard property of inductive topologies. Again, this proposition may be compared with a similar property of Bornological spaces. So the property of being Bornological is also stable under forming inductive topologies. As a corollary, we see that many standard examples of spaces with inductive topologies are barreled. So the following spaces are barreled. For example, we can take the space of continuous compactly supported functions on any topological space T, or the space of smooth compactly supported functions on an open subset of Rn, or we can take the space of holomorphic germs O of k on a compact subset of Cn. Well, they are barreled because each of them satisfies the conditions of this proposition. For example, this space of smooth compactly supported functions, its canonical topology is determined by a family of maps from suitable Frechet spaces to this space. And Frechet spaces are barreled. And as a result, this one is also barreled. And let's recall, let's say that the same spaces are, at the same time, they are Bornological, more or less for the same reason. Metrizable spaces are Bornological, and the property of being Bornological respects inductive topologies, so they are also Bornological. So the natural question is, can we find a barreled space which is not Bornological? The answer is yes. But this is slightly harder. So barreled space is not necessarily Bornological. But it has to be constructed specially, and I'll give you a hint in our next exercise sheet. Bornological spaces are not necessarily barreled because norm spaces are not necessarily barreled. So in particular, norm spaces are metrizable, and all metrizable spaces are Bornological. So this exercise shows that in particular, Bornological spaces are not necessarily barreled. Not necessarily, not always. Actually, we already know that that every complete topological, every complete locally convex space is isomorphic to projective limit of Banach spaces. Hmm? Bound spaces are better than chronological, yes. Yeah, this property is not preserved by projective limits because not all complete spaces are barreled and not all complete spaces are chronological. Okay. So let's now come back to equicontinuity. So we know that if a family of linear maps is equicontinuous, then it is bounded for the topology or any topology of uniform convergence. And now we have a partial converse of this result. This is an abstract version of the Banach-Steinhaus theorem. 1927. Well, formally, Banach and Steinhaus proved this result for Banach spaces. And we'll prove it in a slightly more general setting. Well, the more general setting is most probably to Jordan and Schwarz. If we have two locally convex spaces X and Y, and X is barreled, then every bounded subset in L of xy, which is bounded for the topology of pointwise convergence, is equicontinuous. So let's recall that Ls of xy denotes the space of continuous linear maps with the topology of pointwise convergence. That is, with the topology induced from y to the power x. The topology of pointwise convergence. It corresponds to the case where B, the script B, consists of all finite sets. All finite sets. Well, probably I'll keep the definition of an equicontinuous set. Well, to prove this result, we'll check this condition. We take a neighborhood of 0, V in Y. For convenience, we assume that V is closed and absolutely convex. We can always assume that it is closed and absolutely convex because, well, every neighborhood of 0 contains a closed and absolutely convex neighborhood of 0. And let B denote this intersection. Or all phi in S. So what can we say about B? Clearly it is closed because, well, it's an intersection of closed sets. V is closed, this is closed, and so B is also closed. B is closed and absolutely convex. Because the preimage of an absolutely convex set is absolutely convex. So we want to show that it is absorbing. Why is it absorbing? Well, let's observe that S is, since S is bounded for the topology of uniform convergence, this means that, this means precisely that for every point X in X, the set which was denoted by S of X in the previous lecture. This is just a set consisting of phi of X, where phi runs over S. So this set is bounded in Y. Is bounded in Y. So it is observed by every neighborhood of 0, and in particular it is observed by V. So we can find a positive number lambda such that S of x is contained in lambda V. And if you now take any phi in S, this implies that x sits in the preimage of lambda V, under phi. And by linearity, this means that x sits in lambda B. So x belongs to phi inverse of lambda V. And so, since this is true for all phi, this implies that x sits in lambda B. Okay. So this is true for lambda, and if we get a bigger number, the same conclusion is true, because B is absolutely convex. And so as a result, we deduce that B is observing. B is observing. And so it is a barrel. But X was assumed to be barreled. And so B is, X is barreled, so B is a neighborhood of 0. And this completes the proof. So we have proved that this intersection is a neighborhood of 0, which means exactly that S is equicontinuous. The barreledness assumption here is essential. Well, a standard exercise in functional analysis is to show that this theorem fails in the case where Y is just a base field and X is just a normed space, not necessarily complete. For example, we can take this result fails if X is a space of all finite sequences of numbers equipped with any reasonable norm. For example, equipped with a supreme norm. Supreme norm. Or we can take the L1 norm or the L2 norm. The result will be the same. So the barreledness assumption is necessary. Let's also now briefly discuss a class of locally convex spaces which contains both barreled and chronological spaces. We say that a locally convex space X is quasi-barreled, and some people call them infra-barreled. If every Bornivorous barrel and X is neighborhood of 0. That is an absolutely convex closed set which observes all bounded sets. Well, it's immediate from the definition that all barrel spaces are quasi-barreled. Trivially, and also trivially, all Bornological spaces are also quasi-barreled. But the converse is not true because, well, we know that there exist barrel spaces which are not Bornological, and there exist Bornological spaces which are not barreled. So the class of quasi-barrel spaces is strictly bigger than any of these. And for quasi-barrel spaces, we have the following analog of the Banach-Steinhaus theorem. Namely, if we have two locally convex spaces, x and y, and x is quasi-barreled, then every bounded set S in L of xy, which is bounded now for the topology of uniform convergence on all bounded sets, is equicontinuous. So here, let's recall that LB means that we consider L of xy with the topology of uniform convergence on all bounded sets. On all bounded sets. The proof is an exercise for you because essentially this is a simple adaptation of the proof of the Banach-Steinhaus theorem to the setting of quasi-barrel spaces. So the idea of the proof is basically the same. Okay, let's now discuss a nice application of the Banach-Steinhaus theorem to bilinear maps. First of all, let's introduce some notation. You have three sets, x and y and z, just sets, and the map f from x cross y to z. Then for every x in x, we define a map from fx from y to z, which is obtained from f by fixing one of the variables. And similarly, we define for every y and y, we define a map f sub y from x to z by a similar formula. If now x and y and z are topological spaces, x, y, and z are topological spaces, then we say that map f from x cross y to z is separately continuous. If all these maps fx and y are continuous. Fx and fy are continuous for all x and y. Of course, every continuous map is separately continuous. And it's a simple exercise in topology to show that the converse is not true, even for very nice topological spaces. Now we are interested in the setting of topological vector spaces and bilinear maps. And we have the following result. A theorem. Suppose that we have three locally convex spaces, x, y, and z. Suppose that x and y are metrizable. And suppose that one of them, at least one of them, is barreled. Suppose that either x or y is barreled. For example, a Fisher space. I claim that every separately continuous bilinear map f from x cross y to z is continuous. So for such spaces, separate continuity implies continuity. Before we prove this result, let's prove the following simple lemma, which relates separate continuity to continuity for bilinear maps. Namely, if we have three topological vector spaces x and y and z, and a separately continuous bilinear map, f, then I claim that f is continuous if and only if it is continuous at 0. F is continuous at 0, 0. And the proof is just a short calculation. So what we want to do is to show that this difference is small if x sits in a suitable neighborhood of x0 and y sits in a suitable neighborhood of y0. And we can write this number in the following way: f of x minus x0, 1 y minus y0, plus f of x minus x0, y0, plus f of x0, y minus y0. Well, I hope this is correct. X, y0, these two guys cancel, x0, y, these two guys also cancel, plus this one, minus the same, and minus, okay, seems to be okay. Да? А что хотите добавить? А зачем? Смотрите, мы его здесь один раз прибавили, а потом два раза вычли. Нет, вроде нормально. Эта штука два раза прибавляется, один раз вычитается, а все остальные сокращаются. Okay, and this is essentially the end of the proof, because if f is continuous at 0, then this number is, the first summand is small, if x and y are in suitable neighborhoods of x0 and y0. The second and the third summands are also small by the separate continuity of f. Here y0 is fixed and x0 is fixed. So by the separate continuity, we may make the second and the third summands small. Okay, now let's turn to the proof of our theorem. Okay, so suppose this is not true. Let's assume that f is not continuous. And using our lemma, we deduce that it is not continuous at 0. F is not continuous at 0. X and y are metrizable, so it is not sequentially continuous at 0. And so we can find sequences. There exist sequences in x and y, xn, which converges to 0 in x, and the sequence yn, which converges to 0 in y. And there is a neighborhood of 0 neighborhood of 0 V in Y such that f of xn yn doesn't belong to V for every n. So this means precisely that f is not sequentially continuous at 0. Okay, so to get a contradiction, we do the following. Since f is separately continuous, it follows that. Well, first of all, let's assume from the very beginning that x is barreled. Well, we can easily interchange x and y. So let's suppose that x has barreled. Suppose x is barreled. So for every x in x, f of x yn converges to 0 by the separate continuity. This means that the sequence of the maps f yn converges to 0 for the topology of pointwise convergence on the space. In particular, it is bounded. In particular, the sequence is bounded. Fyn is bounded in the space Ls of xz. And now we apply the Banach-Steinhaus theorem, and we deduce that the sequence is equicontinuous. It is equicontinuous because x is barreled. Да. Ну, значит, просто начиная с какого-то момента сидит в любой окрестности нуля. Значит, конечно, поглощается любой окрестности нуля. Well, the general remark is that if we have a sequence which converges to 0 in an arbitrary topological vector space, and of course it is bounded because it is eventually in any neighborhood of 0, and so it is absorbed by any neighborhood of 0. So it is bounded, so it is equicontinuous, and so we can find a neighborhood of 0 u in x such that for every x in u, f, and for every n, f yn of u, sorry, f yn of x, that is f of x yn, belongs to V. Belongs to V. Let's now look at our sequence xn. It converges to 0 in x, so it is eventually in U. So there is a natural number n0 such that xn belongs to U if n is big enough. So we can substitute xn here, and we deduce that f of xn yn sits in V if n is big enough. And clearly this contradicts our original assumption. This is a contradiction which completes the proof. So as a result, we deduce that f is continuous. As usual, the natural question is, can we relax any of the conditions of our theorem? And the answer is no. All the conditions are essential here. For example, to show that the barreledness is essential, I suggest the following exercise. Construct. So there exist normed spaces X and Y, and separately continuous bilinear functional, that is bilinear map to the base field, which is not continuous. So the barrelness assumption is essential. How about metrizability? Well, the metrizability is also essential. Namely, let's consider the following two spaces. Let X denote k to the power n. That is the product of many copies of the base field. And let Y denote the locally convex direct sum of countably many copies of the base field. We have a natural pairing between X and Y. X cross Y to K, which is given by the following simple formula. And this is a bilinear map. So the exercise is to show that this map is separately continuous, but is not continuous. And also I'd like to stress that both the spaces X and Y are barreled. Let's note that both X and Y are barreled. So X is just a Furché space, so it is barreled. And Y is, well, its topology is the inductive locally convex topology. Actually, this is the strongest locally convex topology. And it is near dimetrizable. So both of them are barreled. This is metrizable, but this one is not. And the conclusion of our theorem fails. So this bilinear map is not continuous. Okay. Another important result related to equicontinuity is the Banach-Low-Glue-Bourbaki theorem. Before we state this result, let's recall that for every topological vector space X, we can define the so-called weak star topology of the dual, namely the weak star topology let's abbreviate it by the following sequence of symbols. Weak star topology on the dual space X prime is the locally convex topology generated by the following family of seminorms indexed by elements from X, where the respective seminorm on F is just the absolute value of f of X. So this makes sense for any topological vector space X. And so in other words, the space X prime equipped with the weak star topology is the space of all continuous linear maps from X to K equipped with the topology of pointwise convergence. So this is LS of XK in our earlier notation. And another standard notation, which was also introduced before, is X prime sigma, or the weak star dual space. So we now have the following result, which is usually attributed to Banach, Low-Glue, and Bourbaki. and I'll tell you a bit more about the history of this result later. If X is any topological vector space, and S is an equicontinuous subset of the dual, an equicontinuous set, then S is relatively weakly star compact. That is, the closure of S is compact. The closure of S in X prime is, for the closure for the weak star topology is weakly star compact. Well, let's prove this theorem. First of all, let's observe that if we embed X prime, the space of continuous linear functionals, into the space of all functions from X to K, then the weak star topology on X prime is nothing but the topology induced from K to the power X. When, of course, the standard topology on K power X is the product topology. That is the topology of pointwise convergence. This is true just by the definition of the weak star topology. So let's now do the following. We take the closure of S, but for convenience, we take the closure not in X prime, but in the whole of K to the power X. So this is the closure of S in K to the power X. And to prove our theorem, it suffices to show that, first of all, the closure of S is compact, and second, that the closure of S is actually contained in X prime. So the closure of S in X prime is the closure of S in the bigger space intersected with X prime. But if it is already contained in X prime, then this is just the closure of S in X prime. Okay, so to prove the first part, the compactness of S, let's do the following. So S is equicontinuous by assumption. So it is bounded for the topology of pointwise convergence in X sigma and X prime sigma. It is bounded for the topology of pointwise convergence, which means exactly that for every X in X, the set S of X, which consists of all numbers f of X, where f runs over S. So this is a subset of the base field, and it is bounded. Is bounded in K. So the boundedness of S for the pointwise convergence topology is equivalent to the boundedness of all these sets S of X for all X. Now, S is obviously contained in the product of these sets over all X in X, just by construction. So now, by the definition of the product topology, the closure of S is contained in the product of the closures of S of X. But this set is compact. This space is compact by Tikhonov's theorem. The product of a family of compact spaces is compact. And so the closure of S is a closed subset in here, so it is also compact. So this proves part one. And now we have to show that it is contained in X prime. That is, it entirely consists of continuous linear functions. To prove this, let's use once again the equicontinuity assumption. So by equicontinuity, there exists Ну, здесь норм никаких нету, это просто произвольное топологическое векторное пространство. Well, so by assumption there exists a neighborhood of 0, U in X, such that for every f in S and for every x in U, the absolute value of f of x is less than or equal to 1, just by the equicontinuity of this set. And let's now observe, this is a very simple exercise for you, that the following two sets are closed in k to the power x. The first set is just a set of linear functionals, of all linear functionals, from x to k. So the property of being linear is stable under closure for the point plus convergence topology. And the second set consists of those maps from x to k, which satisfy this condition. For every x in U, the absolute value of f of x is less than or equal to 1. So both these sets are closed. This is a simple exercise, which essentially follows from the fact that all evaluation maps from k to the power x to k are continuous. Just projections from k to the power x to the respective copies of k are continuous. Okay, now by this condition, we see that S is contained both in S1 and in S2. But S1 and S2 are closed, so the closure of S is contained in S1 and S2. But on the other hand, the intersection of S1 and S2 is contained in the space of continuous linear functionals. S1 is precisely the space of all linear functionals, and for linear functionals, this property implies the continuity. So if we want this to be less than epsilon, then it suffices to assume that x sits in epsilon u, but epsilon u is also a neighborhood of 0. So for linear functionals, this property implies the continuity. And that's it. So we deduce that the closure of S is contained in x prime, and this is precisely our property 2. So this completes the proof. Все линейные функционалы. Все. All linear functionals from x to k. Ну, тут хом. А для хома не было. Ну, окей, well. So what I mean is the set of all linear functionals from x to k. Okay, now the next result is a useful improvement of the Banach-Log-Lobropaki theorem for separable spaces. So suppose that X is a separable topological vector space. And as here, S is an equicontinuous subset in X prime. And I claim that in this case, S is metrizable. And relatively compact in the weak star topology. Not only relatively compact, but also metrizable in the weak star topology. Well, I'll give you just an idea of the proof, and I'll leave the details as an exercise for you. So since X is separable, we can choose a countable dense subset, Xn. This is a dense subset of X. And we consider the following family of seminorms, P, the following countable family of seminorms on X prime given by the following simple formula. So the nth seminorm is the absolute value of f of x. So we may equip X prime with the topology generated by this family, and it is metrizable because there are countably many seminorms. And I claim, and this is a little exercise for you, that the resulting topology of P, which is metrizable, and the weak star topology, which in general is not metrizable. However, both of them induce the same topology on S. Induce the same topology on S. So basically, this exercise completes the proof, because if they induce the same topology on S, we deduce that S is metrizable, because P consists of countably many seminorms, and it is relatively weakly star compact by the Banach-Haloglu-Bourbaki theorem. Of course, I don't claim that these two topologies are the same on X prime. This is not true. They are the same on S, but not on X prime. Usually, tau of P is strictly coarser than the weak star topology. So as a corollary, we see that if X is a separable normed space, then any bounded, I mean norm-bounded sequence in the dual space, the sequence of bounded linear functionals, has a weakly star convergent subsequence. Well, just because it is compact and metrizable, so it is sequentially compact. And since it is sequentially compact, we can always find a weakly star convergent subsequence. In fact, this corollary is precisely Banach's contribution to the Banach-Haloglu-Bourbaki theorem. It was proved by Banach in 1929. And when Banach proved this result, Tikhonov's theorem wasn't available yet. Tikhonov's theorem was proved in the 1930s. So Banach's original proof was different. It was based on kind of diagonal argument. And the Banach-Haloglu-Bourbaki theorem in this form was proved independently by Haloglu, by Bourbaki, that is by Dieudonné and Schwarz, and also by Shmulyan and by Kakutani at the end of the 1930s. Очень много. So this is just a transition. Of course, strictly speaking, we should also add Shmulyan and Kakutani, but well, there are many theorems with this property. For example, the well-known Rees-Markov-Kakutani theorem, which describes bounded linear functionals on the space C of X of continuous functions on a compact Hausdorff space. It is usually called the dual space is isomorphic to the space of complex random measures on X. And this theorem is usually called the Rees-Markov-Kakutani theorem. But in fact, there are many other people who contributed to the proof, but who are not usually mentioned in the statement. So, in particular, Banach and Sachs and some other people, and Radon. Okay. In conclusion, let's now discuss another classical result, which is also due to Banach. Namely, let's discuss the open mapping theorem for Fisher spaces. So to begin with, let's make some simple remarks on open linear maps between topological vector spaces. So you will have two topological vector spaces, x and y. Let's first observe that every open linear map, if T is a continuous linear map from x to y, if T is open, then it is surjective. Well, this is more or less trivial. Well, indeed, in this case, T of y is open and contains 0, so it is a neighborhood of 0. And every neighborhood of 0 in the topological vector space is absorbing. But a vector subspace can be absorbing if and only if it is equal to the whole space. So T of x equals y. So an open linear map is always surjective. And another simple characterization of open maps, a lemma and an exercise at the same time. A continuous linear map from x to y is open. In fact, the continuity is not essential, but we'll use it only in the setting of continuous maps. Is open if and only if for every neighborhood of 0, u in x, its image T of u is a neighborhood of 0 in y. So briefly, T is open if and only if it takes neighborhoods of 0 to neighborhoods of 0. Of course, the left-to-right application is absolutely trivial, and to prove the right-to-left implication, just use translations and use the fact that the topology on a topological vector space is translation invariant. So we can now prove the open mapping theorem. The open mapping theorem, which was originally proved by Banach in 1932. If x and y are Fisher spaces, then every surjective continuous linear map from x onto y is open. So we already know that every open map is surjective. So in the setting of Fisher spaces, the converse is also true. The proof of this fact is naturally divided into two steps. So to prove the first part, we need the following auxiliary definition, namely if x and y are topological vector spaces and T is a continuous linear map from x to y, then we say that T is almost open. Almost open if for every neighborhood of 0, u in x, the closure of T of u is a neighborhood of 0 in y. So if we compare this definition with our lemma, we see, of course, that every open map is almost open. And simple examples show that the converse is not true. Already in the setting of normed spaces. So we have the following lemma, lemma 1. If we have two locally convex spaces, x and y, locally convex spaces, such that y is barreled. Y is barreled. And suppose that T is a surjective continuous linear map from x onto y. I claim that T is almost open. T is surjective, then it is almost open. The proof is just a line. Well, indeed. We check this condition under the assumption that U is absolutely convex. So suppose that U is an absolutely convex neighborhood of 0. We look at the closure of T of U and observe that this is a barrel. In Y. Well, indeed, why is it a barrel? T of U is absolutely convex, so T of U is also absolutely convex. And it's a simple exercise to show that the closure of an absolutely convex set is also absolutely convex. So it is absolutely convex, it is closed by construction, and it is absorbing because T is surjective. Already T of U is absorbing, and the closure of T of U is also absorbing. So it is a barrel, and Y is barreled, so it is a neighborhood of 0. And that's it. Lemma 2, this is the second part of the proof. Suppose we have two metrizable locally convex spaces such that one of them is X is a Frechet space, X is a Frechet space, and Y is just a metrizable locally convex space. Now the completeness of Y is not relevant. I claim that every almost open continuous linear map is open. Almost open T from X to Y is open. Well, why is it so? So both X and Y are metrizable, and we know that a locally convex space is metrizable if and only if its topology can be generated by an F norm. That is a function which is something like a norm, but not necessarily homogeneous. So let's choose such norms. So this is an F norm on X, which generates the topology. On X. And let's introduce the respective open ball, UR, the open ball of radius R in X centered at 0. And we will use the same notation for the space Y. Y is also assumed to be metrizable, so we keep the same notation for Y. Okay, now we assume that T is almost open, and so for every positive R, we can find a positive rho such that the closure of the image of the ball of radius R contains the ball of radius rho. Now to complete the proof, it suffices to show that if we slightly increase the radius here, for example, replace R by 2R, then we have the following inclusion. So clearly this inclusion will imply that T is open. Well, why is it so? Let's use once again the assumption that T is almost open. We can choose a sequence of positive numbers. Непонятно где. Вот отсюда? Well, X is metrizable. Okay. So we know that a locally convex space is metrizable if and only if its topology is generated by an F norm. And F norm is something like a norm which is not necessarily positive homogeneous. So we just use the following notation for the ball of radius R. Okay. And of course we can use the same notation for the space Y because it is also assumed to be metrizable. Okay. Now, well, this is, let's look at, where is it? At the definition of an almost open map. So we apply T to the open ball of radius R. So the closure of the set is a neighborhood of 0. Since it is a neighborhood of 0, it definitely contains an open ball centered at 0. Okay? Just because it is almost open. So if we prove this inclusion would imply that T is open by our lemma. So? Okay. So now to complete the proof, we want to prove this inclusion. Okay. So how do we do it? We choose a sequence of positive numbers, say rho k. Each rho k is positive, and the sequence converges to 0, such that the closure of the image of the ball of radius R over 2 to the power k contains the ball of radius rho k. Well, this is possible, again, because T is almost open. Now let's take an arbitrary Y in this ball. And let's approximate it by an image of a vector from here. So there exists x1 in UR such that the distance between y and tx1 is less than rho 1. Here we are using this assumption. Now, this vector sits in the ball of radius rho 1. So by this property, we can approximate it by the image of a vector from here. So we can find a vector x2 in U radius R over 2, such that y minus tx1 is approximated by tx2, for example, in this sense, such that this is less than rho 2. And so on. So at the kth step, we find a vector xk in the ball of radius R over 2 to the power k minus 1, such that y minus some tx I from 1 to k is less than rho k. And so on. So we have constructed a sequence with this property. Let's now look at the following series from 1 to infinity. So it can be estimated like this. So x1 sits in UR. This one sits in UR over 2 and so on. So this is strictly smaller than R over 2 to the power k minus 1. And the sum is equal to 2R. And in particular, it is finite. So the series is absolutely convergent for the F norm. Now the usual triangle inequality implies that the sequence of finite sums is Cauchy. And so the respective series converges. There is an element x in X, which is the sum of the respective series. And moreover, this estimate shows that this vector sits in the open ball of radius to R. And if we now come back to this estimate, let's mark it as star, and if we let here k go to infinity, we deduce that, well, this guy goes to t of x by the continuity of t, and this goes to 0. So as a result, t of x equals 1. So this estimate implies that y equals t of x. And this completes the proof. This completes the proof, so we have proved that, we have proved this inclusion. Okay, so an equivalent form is the so-called closed graph theorem, which you probably know for Banach spaces from your functional analysis course, but also it holds with the same proof for Fauché spaces. If x and y are Fauché spaces, and T is a linear map, then T is continuous if and only if its graph, gamma T, is a closed subspace of the product. So a standard exercise is to prove the closed graph theorem and to show that it is actually essentially equivalent to the open mapping theorem, namely to deduce the open mapping theorem from the closed graph theorem. So in fact, they are equivalent. Well, it's time to finish. Just one final remark. I will not write anything, just I'd like to state a little open problem. Maybe it is open only for myself, but anyway. So let's look once again at the proof. So we assumed this inclusion, and we proved that if we replace R by 2R, then we have a similar inclusion, but without the closure. In fact, we can do better. We can show, more or less the same argument shows that for every positive epsilon, the image of the ball of radius r plus epsilon contains the open ball of radius rho. This is a very simple exercise. Also, it can be shown that in the setting of norm spaces, we can do better. For norm spaces, we can show that the image of the open ball of the same radius contains u rho. So we can just remove the closure here. So the open problem, a little open problem about open maps, is that can we achieve this inclusion in the setting of Fauché spaces? So does this result hold for Fauché spaces? I wouldn't say that this is very important, because what we really need here is that T is open, and it's not very essential what the actual radius of the ball here is. But anyway, it's quite interesting to prove if this is true for norm spaces. Maybe this is also true for Fauché spaces, but I don't know how to prove this. Да, в образе. Если он лежит в замыкании образа шара, то он лежит в самом образе шара. Вот так. Okay, so that's all for today.